This video aims to uncover the contributing factors in a functioning DC motor, starting with a step-by-step procedure. I cut out the necessary portions for the base and the stator walls for later on. A base ensures the motor can be portable. Moving on to the shaft, I took advantage of a 3D printer at home to process a lightweight product which lowers the threshold of torque. I proceeded to manipulate two paper clips in such a way that suspends the shaft above the ground whilst ensuring a stable spinning action. Addressing this, the shaft had indentations on both ends. Using copper wire, I wound 50 turns on each side of the armature, encompassing a reasonable area per turn, whilst respecting the proportions of a small design. This functions as the electromagnet. Crucially, these factors contribute to higher torque, as we refer to the formula. Extra caution when crossing over because both arms should be wound in the same direction. After coiling, I cut the end of the wire and sanded both overhanging portions to remove the insulating coating. A current carrying conductor in a magnetic field will experience a force. Its direction can be determined by the right-hand rule. Applying to this situation, AB experiences upward force while CD experiences downward force. This produces clockwise rotation as viewed from the terminal. The split ring commutator is essential in a DC motor, and here's why. Without splits in the commutator ring, the rotor would eventually stall at a quarter turn due to said portions constantly experiencing a force in their respective directions, even after crossing the vertical plane. Now theoretically, the lack of conductivity at this phase is detrimental to motor performance, but inertia ensures the rotor doesn't stop spinning. The third phase sees conductivity recommencing, but the current is now reversed. There are two ways of interpreting it, as shown on screen. Either way, AB now experiences downward force and vice versa for CD. Therefore, torque is applied in the same direction as half a turn ago, with increased RPM being the beneficiary. Torque is maximized when the area vector is perpendicular to the magnetic field. Hence, I've aligned my commutator where it will contact the brushes at that instant, and then finally taping it down. I manipulated two more paper clips to act as brushes, ensuring they undergo contact with the commutator to input current into the electromagnet. I then stacked magnets and tacked them onto the stator walls to increase magnetic field strength. Since B is inversely proportional to the distance from the wire, fixing the stator at the shortest plausible distance was paramount to maximize torque and force. In the power supply, two 6-volt batteries wired in series to input 12 volts to increase the current. Now we have a fully functional DC motor. How good! But with constant rotation, the magnetic flux is changing through the area of the coil as cos theta of the area vector changes. So we need to address Faraday's law of induction, where an EMF completely dissociated with applied voltage is induced by a change in flux. This intuitively poses a challenge against the law of conservation of energy. But consider this, Lenz's law states that an EMF will induce a current in the electromagnet, which produces a magnetic field that opposes the initial change in magnetic flux. So that electromagnet will obtain electrical energy as a result of this induced current. Given a fixed quantity of total energy, this irrefutably reduces kinetic energy. Simply put, some of that kinetic energy is converted to electrical energy to satisfy Lenz's law, but since that net energy remains constant, energy is therefore conserved. Applying this in the motor situation, the EMF produced in the electromagnet will oppose the direction of the source EMF. With this, the net EMF will have less voltage than the source EMF. Furthermore, the back EMF is strictly dictated by the rate at which the flux is changing, and therefore depends on the electromagnet's RPM. Observe that when the RPM changes by a factor, x, the amplitude of the rate of the flux change is multiplied by x. A faster spinning rotor would induce a stronger back EMF, and according to this equation, the current would decrease. Imperatively, back EMF allows the motor to self-regulate its RPM. Playing through the variables, a load increase will initially decrease the RPM, and consequently, back EMF decreases due to proportionality. This allows the current to increase, given by the current equation. Higher current equates to higher torque, and then higher torque increases the RPM due to proportionality, therefore approaching equilibrium. These variables experience the exact opposite in a load decrease, but will also approach equilibrium. Finally, should a motor undergo excessive load or not rotate fast enough, it is prone to motor burnout, according to Joule's first law, since there is no back EMF to negate the high current, which will still circulate anyway. Resistors connected in series can counteract this by maximizing resistance as the motor starts. And now you are a DC motor expert.